Okay, so let me ask few things, from you people. So probably,
I don't need socks. I don't need them.
okay. So what I was saying actually, so there are a couple of Amna Said, how are you? Tahura, can you hear me?
Sir.
Sorry, I cannot hear you.
Assalamu alaikum, sir.
Walaikum assalam. How are you?
Sir, I'm fine, alhamdulillah.
Good. Okay, so I don't know, in Pakistan always there is a net problem. It depends on the region actually. I don't see all the students here, even though they claim that they are taking, but anyway. Okay, so I want to ask few things. Let's suppose if you have helium neon laser. Okay. So this helium neon laser, if you have, let's suppose, and it's a red color, or can be green, depends. Let's suppose its power is in milliwatts. Okay. So what you people can do with this laser? You want to use somewhere where you can use. First thing is that you people need to know that the helium neon laser is pulse laser or CW. Okay, so okay, so Dargis, can you please tell me the helium neon laser is a CW or pulse laser?
Sir, it's a CW laser.
Okay, so if you want to use where you can use it.
Sir, we can use in the purposes where we want a continuous intensity. Means maybe where in any applications where we want a continuous like bombardment or like this kind of scenarios. Then we can use.
Yeah, not for bombardment. Bombardment, you need pulse laser.
No, actually, I'm not getting a word for what is the precise word means.
Okay.
Like the cutting. I think for the cutting of some
Yes.
metal for material, we need a continuous intensity or energy there, so we can use it.
Yeah, you are right. For the cutting, you can use a CW or pulse also can be used, but helium neon is not used for cutting. Actually, it's very low power. So probably we can use it for if you want to see the interference fringes in Michelson interferometer, in Newton's ring experiment, or something. It depends. If you have power.
Can it be used for like medical purposes where we need like precision but low intensity? I think.
No, medical, no. Helium neon is not used in medical. There are a number of reasons. We use in the medical other CW like carbon dioxide and some fiber lasers, and but not helium neon. Okay, because this wavelength is not suitable for any kind of medical treatment. Okay. So
it's a red color, a red or green.
Yes,
636 nanometer.
Yes, green is very less, but mostly it's red. So that is why. So, Ihtisham, how much? Ihtisham?
Yes, sir.
Have you seen the helium neon laser?
Sir, can you repeat your question?
Have you seen the helium neon laser?
No, sir. Actually, not in real. I have seen it. I mean, in videos and these things.
Okay.
I haven't
No, but
not used it.
in any kind of undergrad lab or somewhere in the university?
No, sir. We didn't have any laser. Actually, in my university, there were very limited equipment, so there was not a presence of any laser type component.
So which was your university?
The University of
Oh, University of what? They don't have helium neon lasers?
Sir, at my time, they didn't have any kind of laser.
Okay, okay, okay.
Sir,
So, who is it?
Mudassir was also from Salman is here.
Yes,
Assalamu alaikum. Mudassir was also from.
Yes, Mudassir was there, definitely.
Mudassir was my junior.
He was your junior, so you were senior.
Yes, I was senior, 1 year ahead of him.
Okay, okay. So why university is still like this, or it's improved a bit?
Sir, actually, it's a long time we didn't go there. I mean, I didn't have a chance to visit there, so I don't know what's going on there right now.
Okay, 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 okay. So Salman, have you seen the helium neon laser?
Yes, sir.
Helium neon
Why
laser.
not? Yes, sir.
Yeah, definitely
I
you must
use
have
it
seen.
also.
You use
Yes,
it.
sir.
So, I mean, where can we use this helium neon laser?
Sir, we can use helium neon laser for different purposes, like for the imaging purposes. We can use helium neon laser where we want a low power light. Like I used it in during my MS research for the lensless images, and also we can use it in other experiments, like in labs, because in labs we do not need high power laser.
Yeah. So, I mean, you can also use it for the holography. This
Yes, sir.
helium neon laser.
Definitely for the holography purposes.
Yes, 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 yes. Okay. So, I mean, if we let me go to next, Ali.
Yes, sir.
If we want to, I mean, if we have a helium neon laser, but we want helium neon laser to be in a pulsed form, long pulse, but pulse form, what can we do?
Sir, I think we can use mode locking or Q switching.
You see, you didn't understand the lectures. You didn't go through properly. Mode locking is a very advanced kind of thing. Mode locking and helium neon laser is far, far, far. Yes, Q switching you can use, but let's suppose if you don't have many things in the lab, and how can you? You want to have one pulse of laser like after 1 second, 2 seconds, 3 seconds. What can you do?
Sir, it's like maybe we can use a shutter or spinning wheel, like that thing I just saw right now, few minutes ago. In order to stop the pulse for some time and then let it allow to pass,
Yes, you
which
are
can be
right.
done manually.
Yes, we can do is you can use a chopper. Okay, so to rotating wheel, something like, yeah, you can use this form, and definitely. So Mauricio, you must have seen the helium neon laser.
Yes, for some experiment.
Yeah. So what kind of helium? How much power you use?
Well, I didn't see that how much power, but because it's all set up in a in a device. So
Yes, yes.
I think it's milliwatts.
Yeah, definitely. It's
was
helium. Yeah. So, and you use in a green color or red color?
two color.
A red color. Mm. And what else? I mean, which laser you use in your experiments other than the helium neon laser? Did you use any other laser?
The solid state laser, infrared laser.
Okay, solid state, which? ND-YAG or what exactly?
Yes, and the to um, to irradiate some red earth ions in nanoparticles.
Okay, okay. Good. Okay, Tahura, can you hear me? Tahura.
No. Assalamu alaikum, sir.
Walaikum assalam. So Tahura, how is going?
Sir, good.
Your net is okay?
Sir, not very good, but there is a
Big,
signal issue.
yeah, because I tried to ask you before, but I couldn't get any reply from your side. So Tahura,
Sorry, sir.
yeah, it's okay. Tahura, tell me, have you seen any kind of laser?
Actually, sir, I didn't see, but in picture, I see a simple laser or not that much in
You are
real
going,
life.
okay, so you are going to start your master's now.
Yes, sir.
Okay, so you may take some laser courses there.
Yes, sir.
Okay, so probably maybe, I mean, if I ask you that Andy Yag, I taught this Andy Yag about the Andy Yag a little bit. So Andy Yag laser, is it CW or pulsed?
CW, sir, I think.
Sorry? So
CW laser.
yes, CW. So if we want to make this CW laser to a pulse laser, what can we do? We have Andy Yag laser.
Sir, Q switching, yeah, or
Yeah.
mode locking. These two methods, I think.
Yeah, Q switching you can use for a mode locking. This gain medium, laser medium is not suited. You can go back to my lectures and you can find out that why it's not suitable mode locking stuff. Mode locking is an advanced kind of thing actually. So there are many things that you people need to understand actually what is mode locking. My previous lectures or something like this. And
Yes, sir.
yeah. So Amna Said.
Yes, sir.
Have you seen any laser?
Sir, I visited a laser lab and I saw their lasers, but I don't remember now that it was which type of laser.
And I think you are from KPK, isn't it?
Yes, sir.
Peshawar University.
Yes, sir.
Do they have the laser in Peshawar University?
No, sir. They don't have a laser lab.
In Peshawar University, you don't have a laser lab? It's very
No,
old
sir.
university, I think. It's very old university. Salman? Salman, are you there?
Yes, sir.
Yeah, Peshawar University is very old university, isn't it?
Yes, sir. Very old.
They don't have a
Like
laser?
75 years have
Yes.
been completed.
They don't have a laser laboratory there, laser facility. They don't have. It's in your region, I mean, somehow.
Sir, I visited their labs, I think, one time for the nuclear research when we were there for to calculate the lifetime of different. One time I visited there, but I don't think maybe they have the Hini laser, because in Islamia college there were any laser.
Okay, okay. Islamic College is university now, isn't it?
Yes, sir. Both are in one campus.
Both are in one campus.
Yes, sir.
So in
One boundary.
Okay. So in KPK region, Amna Said is also from KPK region. So actually there are many. Tahura and Tahura is also from KPK, isn't it?
Yes, sir.
Yeah. And
Tahura Urusa.
Arusa also. So there are a couple of students from KPK region, mostly from KPK actually.
Sir, Urusa's BS was from Shahid bin Nazir Bhutto University.
Where it is? Where it is?
Waveni University in Peshawar.
Okay.
Yes, sir.
And how many universities are there?
I think the government universities are four universities. Government universities. No, 5.
Okay.
And others are private, like Ikra University, Sikaz University, City University, Sarhad University.
Okay.
These are private universities there. In Peshawar, not in KP. KP have many universities.
Yes, I know that.
Like in Mardan, Malakand.
Yeah. Okay, anyway. Amna Said, so probably you may see in future the kind of laser. But you are checking this. Yeah.
The reason is Amna Said may have not seen the laser because in KPK people are not interested in the laser. In quantum, very few people are interested, and also in laser field.
So what?
Here, most of the people are interested in the material science because their research are very easy, and they can easily get through that. They can easily publish their research papers. That's why the professors motivate them to take the material science.
So probably Amna Said may also do the same thing. Yes, Amna Said?
No, sir. I actually did my BS from Quaid-e-Azam University.
Okay. So then you must have seen that the laser.
Yes, sir. I visited
so why
the laser
we
lab.
Have discovered Peshawar University so much?
And why did you start your MS there in the Quaid University?
Sir, it was a mistake.
Okay. Anyway, okay, let's move forward. And I want to ask David. I mean, how many laser have you seen in your lifespan or during your university time? Okay. Okay, fiber laser as well. And so in Mexico, almost all the university, they have the lasers and laser facilities. Okay. And there are, I mean, like facilities of ultrafast laser as well in Mexico. So the labs are laser labs are well equipped. They have Yes, yes. Okay. Yeah, I remember that dye laser. Yeah, dye laser is very messy kind of things. So it was in your university? Ah, okay. 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 Mm-hmm. Okay. Okay. Mm-hmm. Okay. Okay, let's start the lecture now. I just want to see if, anyway, it's good that to have a chit chat with the students. Okay, so you people can see or not?
Yes, sir.
Slide.
Visible. Visible.
Okay.
Lecture 12.
Okay, so the lecture 12. So last lecture actually, we studied about the mode locking stuff. Actually, mode locking was started from lecture 11 actually, and for lecture 10 probably, and some kind of different mode locking techniques. The last lecture we studied about the saturable absorber or Kirlan's mode locking, and before that we use uh, electro-optic switches in the cavity to have mode locking or something like this. So as I mentioned that the mode locking is the most important thing, and mode locking is finished. Now we are moving forward. Even though mode locking will be, coming again and again. But now we are going to study that how can we generate ultra fast, ultra short, ultra fast, or femtosecond pulses. But before to start, one thing probably I would like to mention here, and you people already know, that dispersion. You know, the light is dispersed when it passes through a certain mediums. Okay. Like if it is passed through the prism, it dispersed. Grating also. And even from a simple transparent material, if it passes, it disperses as well. So the major problem in ultrafast laser, because of its broad spectrum, the effect of dispersion is very prominent. And it is supposed to be controlled. If we cannot control this dispersion kind of things, then probably we cannot achieve the ultra short pulses. Okay, so let's move forward. Let's revise few things here. So these things, I assume that you people already know that, but I would like to revise here that what is milli, what is kilo, micro, mega, nano. Because whenever we move to the ultra short pulses, okay, so ultra short pulses mean very short pulse, even though it start from picosecond, but mostly femtosecond or something like this. So we need to know these kind of units. Usually, you know that in case of milli is 10 to minus 3, micro is 10 to minus 6, nano is 10 to minus 9, pico is 10 to minus 12, and 15. Minus 15 is a femtosecond. Okay, so this blue portion actually, this is ultra short category. And attosecond is minus 18. But attosecond pulses cannot be generated directly. Like a femtosecond pulse, we can generate directly. Attosecond pulses are different kind of pulses. I mean, these are pulses, but you cannot generate directly. You need to generate indirectly. Indirectly means you have to probably, I don't know how to say it. You have to generate kind of higher harmonic generations, higher harmonics, and then convert into that. But anyway, this is complicated. So we are here now. Okay. And when you have a small pulse, you have a huge peak power. Okay. So huge peak power, like you can see here, for kilo 10 to plus 3 actually, and for mega 10 to plus 6, 9 giga is 9 actually, and tera and peta and exa. So this is the range when we study the ultrafast laser. So usually we deal with terawatt power or petawatt power. Giga can also be, but because the pulse is very short, when the pulse is very short, so the spectrum is supposed to be very broad, and all the power concentrated in a small, very, very small time interval. So we get very high peak power, that is terawatt and petawatt. So terawatt, I mean, if you make a simple laser system, simple mean ultra-fast laser system, with 1 or 2 amplifiers, you can achieve terawatt very easily. For petawatt, you have to do something special because petawatt is huge power. And for this one, you need maybe multiple amplifiers or something like this. Okay, so how to prepare femtosecond, or you can say ultra short pulse? Prepare. I mean, we need to have, if you read here, large spectral bandwidth. Okay. Large spectral bandwidth, large spectrum. Okay. Like here you can see. In case of a normal laser, you have like this kind of the spectrum. And in case of ultra short laser, you have like this kind of spectrum, broad spectrum. Okay. And like here is a nanosecond. And you can see here femtosecond, the spectrum. What is spectrum? Intensity here, and the wavelength. Okay. So if you have a spectrometer, which you can find in all the laser labs, even in the some undergrad labs they also have. If you take a light, any light, and you shine the light on the slit of the spectrometer or the usually connected the fiber, then you can see this kind of spectrum. Okay. And spectrometer, I assume you people know spectrometer, not all, but maybe most of the people know about the spectrometer. And probably they have seen, like Salman must have seen, David must have seen, Mauricio must have seen, and Adnan Sami, I also assume that he has seen, even though he's very rare. Adnan, you are here? Okay, so spectrometer, basically, what is spectrometer? I mean, you shine the light on the grating, okay? then it disperses the light, and then it's recollimated again to get the spectrum on the slit or something like this. But anyway, the spectrometer is not a topic here. Topic is to tell that in case of femtosecond laser, you have a wider spectrum. In case of nanosecond laser, you have very narrow spectrum. Okay, and this is what it shows here. The time, and this is the spectral width. In the temporal domain, in the spatial domain, okay, and is approximately equal to 2 pi. Okay. So you can apply like uncertainty principle. Okay. So you don't need to consider this 2 pi at the moment, okay, because it's a time bandwidth product. Time bandwidth product. My previous lecture I have not explained, but I mentioned this thing a bit. So the first thing, to prepare the femtosecond laser, we need to have a broad spectrum. Okay. For a broad spectrum, we need to choose a gain medium who can have a broad spectrum. Okay. So let's assume here that this there is one mistake actually, if you notice here. Who will point out this mistake? Yes. This is not, yeah, this is not T here. This is not T. Okay. So this is your spectral bandwidth. Okay. Let's suppose this is omega actually. You can say, or lambda also you can say. Okay. So the spectral bandwidth is 21 nanometer, and the temporal bandwidth, which is this one, is 50 femtosecond. Okay. And the center wavelength of the spectrum is 800 nanometers. So in easy words, to prepare the femtosecond laser or ultra short laser, you need to have a broad, very large spectral bandwidth. Okay. And it depends on the gain medium as well. So broader the spectrum, shorter will be the pulse. Okay. And the standard or the conventional ultra short or femtosecond laser, the center wavelength is 800 nanometers. Okay. If you have this spectrum like this, the center will be here 800 nanometers. Okay. And this is your wavelength. So this center will be 800 nanometers. So ideally femtosecond pulse, they have like, if you have a spectrum of 29 nanometer broad, 21 nanometer broad, then you can get around 50 femtoseconds possibility. There are many factors involved, but imaginary, we can say that we can have around 50 femtosecond if the spectral bandwidth is 21 nanometers. Okay. So if you go down of this slide, you can see this yellow portion here. Large bandwidths limit the choice of laser active medium. So not all the laser medium like ND-YAG or even other, they cannot have a very broad spectrum. Okay. So the gain medium has to be like titanium sapphire, or like here the titanium sapphire, or the laser dyes. Okay, so if you have titanium sapphire or dye medium, then you can have a broad spectrum to generate the femtosecond pulses. Okay. Otherwise, not all the mediums, the gain mediums, they cannot produce, because the spectral bandwidth of these for TICEF and laser dyes are not enough to generate the femtosecond pulses. And after that, first thing you have to choose that the gain medium, suitable gain medium. Okay. And second thing, laser cavity design. So cavity design here. And the third thing, dispersion management. Okay. So to prepare for a femtosecond laser, what you need to like choose a gain medium, broadband gain it should have, and the cavity design, and then dispersion management. So if you can manage all these things, then you can generate the femtosecond or ultra short pulses. Okay, so let me move to the next slide. Okay. The basic principle, which I mentioned before as well, that mode locking is must. This thing include in the cavity design, okay, and the dispersion compensation or dispersion management. So what do you see here? There are two mirrors, HR and output coupler, and you have here the pump, obvious, and the gain medium, and here you have mode locking, and here you have dispersion. So pulse has to be mode locked, and this mode locking has to be in the cavity. Okay, so mode locking mechanism can be a hybrid type, can be active, can be a passive. It depends. And dispersion compensation, how we disperse the thing, we also compensate in the same way. We can use the prism, we can use the gratings to introduce or to compensate the dispersion in the gain medium. Not in the gain medium, in the cavity. So basic components, you know that already. You need to have a cavity, you need to have a gain medium, you need to have a pump. Okay. And now to prepare for the femtosecond or ultra short pulse, you need to have a mode locking mechanism arrangement in the cavity and dispersion compensation. In case of a normal laser, you don't need mode locking, or you don't need also dispersion compensation. Simple cavity you can generate. But in case of femtosecond or ultra-fast laser, you need to have mode locking mechanism and dispersion. Without mode locking, you cannot have pulse laser. And the second thing is dispersion. And if the dispersion is not controlled, then you cannot have shorter pulses. So here, this revisited or revised the thing which we have already studied, that is saturable absorber. You know that this is a passive technique which is used to have a mode locked pulses. Okay, so what saturable absorber does actually, you know that at a low intensity it absorbs the pulse, and at higher intensity it bleeds and it releases the pulse. Okay, so it means that the peak pass through, and the tail and the bottom portion of the spectrum, it will be squeezed, it will be blocked. So we can get in this way a shorter pulse. Go back to my previous lecture, you can understand more how saturable absorber works. So let's suppose that this is a pulse, another pulse, another pulse, another pulse here, another pulse, another pulse. So what difference do you see here? So it makes number of round trips in the cavity, and saturable absorber is there. Okay, and with the passage of time, we get this pulse. In the beginning was this one. Okay, it was blocked kind of, and this one also blocked this portion. This one also blocked. So you can see slowly, the low intensity, it absorbed this portion. And we get only the peak portions. Okay, so understand this thing, go back to my previous lecture, how it works. Okay, this is just to revise a bit or revisit it again, because whenever we make or whenever we want to generate the femtosecond or ultra short pulses, we need to have more locking mechanism in the cavity, and more locking mechanism, as I mentioned, it can be like active, passive, it depends. So passive is more popular and easier, you can say. So this is one of the passive method. Okay, so the same thing is mentioned here. The weak pulses are suppressed and the strongest one is amplified. Okay, the strongest is bleached and it passed through the saturable absorber and it amplified. And the low intensity pulses, they are definitely suppressed. Okay, and also you can see here that the leading and the trailing edges here, are weak, so that is why these are eliminated here. Like this portion, this portion. Okay, so in this way, saturable absorber, it yields a very short pulse. Now, as I mentioned that to have a broad bandwidth, spectral bandwidth, you need to have a certain gain medium. And titanium sapphire is one of the medium. There are more now actually, but the popular and famous one is titanium sapphire. Before, people were using the dye medium. Dye medium, as I mentioned, that it's dye liquid, and this dye liquid is like rhodamine 6G or something like this. Similar kind of dyes you people use to dye different clothes and hairs as well. And so people were trying to get ultra short, ultra fast pulses using this dye medium, dye gain medium. Okay, and this is your gain medium here. Okay, and pump is always needed. So this is your gain medium, which is a dye, and it's pumped. And for the mode locking, they use a saturable absorber. And this kind of experiments or this kind of laser generation was used to be in 80s and 90s. Okay, 80s and 90s. In the 90s, actually, they somehow discovered the titanium sapphire, but still people were working on the dyes to generate the short pulses. So this is this kind of arrangement is not for to generate the femtosecond pulses, but it to generate the picosecond pulses. Still, the picosecond pulses in the same category of ultra fast, ultra short lasers. Okay, and later on, they also use this gain medium, the dye gain medium, to achieve tens of femtosecond as well, but it was really few groups they could do and reported this thing. Because in case of a dye, there are many things which are not good for human health. And it's dirty. It's kind of dirty work in the sense that the lab get dirty. You have to fill up the dye in the cuvette kind of thing. And So, and also it's not good for the hands and for your body. Messy, basically it's messy. And dye, that is why the people have the dye medium. Maybe some places are still there, like David mentioned, there, but it's not very much, excuse me, it's not very much practical in these days. Okay. If you remember, in the last lecture, we studied more locking definitely technique to use a passive in the passive category, that the Kerr lens more locking. Okay. So higher the intensity. So if the intensity is higher than the refractive index effect, okay, of the medium, you can see here this equation, if you remember, that refractive index here, okay, this is also refractive index of second medium here, refractive index, this is intensity, and this part of the equation is very important. Go back to my previous lecture and you can understand. So N varies with the intensity. Okay. So this is a basic equation for optical Kerr effect and Kerr lens mode locking. So because of this, this portion of the equation, we can have some of the gain medium that can act like a saturable absorber. We don't need anything in the cavity, but the gain medium itself will help or will be able to generate shorter pulses and having more locking technique. That is because of the Kerr lens, Kerr effect. Okay. So here, if you remember in the last lecture, I mentioned this thing and it's animated also somehow, that the low intensity, when it pass through the gain medium, which is, we are saying here about the titanium sapphire. So that the low intensity will pass through as it is, no effect. Okay. And this is aperture, a kind of aperture or pinhole or whatever you can say, it's aperture basically. So if the intensity is low, it will pass through the crystal, which is a gain medium, and the losses are very high because we don't get at the output anything. But if the light intensity is very high, when it passes through this medium, which is a titanium sapphire, and because of this effect, this one, self-phase modulation, self-focusing, this is a phenomenon. Go back to my previous lecture, you can understand more. This is just a revisited or revising kind of things. So in this case, we have like effect which occur, and we observe the phenomena of self-focusing of the laser light. And this is a gain medium, which is titanium sapphire. And this phenomenon we observe only if the intensity is very high. If the intensity is low, not probably, I mean, you may not be able to observe self-focusing. So self-focusing is a very important here, and because of this self-focusing, you have more locked laser. And go back to my previous lecture again, I would say. Okay. This is a continuation of that thing because it's kind of lens is created, virtual lens inside of the medium. Okay, and low intensity beam, it will not have any effect. Okay, high intensity will observe of self-focusing. Okay, and this is one of the reasons that is because of this effect actually here. This we observe that it is kind of saturable absorber. The same phenomena happens here. Okay, and high intensity, it's more focused, and as compared to the low intensity, this is low intensity, this is the high intensity. Okay, and perfect overlapping you can observe in case of a high intensity, and but in case of a low intensity you don't observe this kind of things. Okay, and these low intensity waves are, that is why we use the aperture here. Okay, and the low intensity light, it also block, so we only get what we need at the other side of the aperture. Okay, so what you see here, so again, this is your simple cavity. Okay, and it has a gain medium, it has output mirrors. Okay, so in the case of pulse laser, the laser, it emits the train of identical pulses. Okay, the train of identical pulses you will see here, like this is one of the pulse here. Okay, and inside the cavity it will move to and fro here. We get the output at the output mirror side. Okay, and what we get at the output, you can see here, this train. Okay, equal intervals after equal, it depends on the length of the cavity. Okay, and okay, so equal intervals depends on the length of the cavity. That is very important. And what else things are there inside the cavity for the mode locking. Okay, now what is this T actually here? If you see this T, the time between the pulses, 0T, 2T, 3T, whatever. So the time between the pulses, this one, identical pulses. Okay, so this time interval is same for all the pulses. Okay, and now these are identical short pulses. Okay, so what do you understand from here? Sometimes this WhatsApp actually disturbing a lot. People are sending the messages. Anyway. Oh. Okay, so the thing is that here you have a medium inside the cavity, And what we are saying here is a pulse laser. Okay, so pulse laser mean there may be some mechanism, okay, that generating our pulses, that is mode locking or something like this. Okay, so in this case, what exactly happened? At the output, you get these pulses, identical pulses. Okay, at the output. Now, if we move before to move to the next slide, if you remember, uh, let me have a 1 minute break because Azan is going on. Okay. Okay. Sorry for inconvenience. So before to move to the next slide, as I mentioned that because we are dealing the broad spectrum, try to understand what I'm saying. Maybe it's difficult for you people to understand, especially the young ones from Pakistan. But try. So We are dealing with a broad spectrum. When the broad spectrum is there, then you have to think about the dispersion. Okay. And dispersion is simply like you have seen that if the light is coming from somewhere, just a moment. Like light is here and you have a prism and the light will spread into colors. Okay. Dispersion. So this input light, it has a very broad spectrum because it's a white light. It's not a laser, it's a white light. Okay, that is why it's converted to the these 7 colors or something like this. Same thing happened with the femtosecond or ultra short or ultra fast laser, because its spectrum is broad. When it passes through, if you have a prism, then you can see its spectrum become like you can see some colors here as well in this case. So this dispersion. So this dispersion, I mean, it exists, but we have to compensate in some way. And this compensation, like how we can compensate this, we will see. But first thing is that we need to know that what is this dispersion. Have you heard the phase and the group velocities? These kind of words, have you heard about it? The phase and the group velocity. David, have you heard about it? Okay.
Sir, I
Yeah. Okay, Salman, do you know?
Yes, sir.
Good. Okay, so Ali Hassan, the businessman. All the people know what is this phase velocity and group velocity? Tahura.
Yes, sir.
Sir,
Okay.
I know.
Okay, good. Okay, so this phase velocity and group velocity are very important somehow to know. What do you see here in this animation? That group velocity and the phase velocity. One is envelope, the electric field, okay, and the carrier. So if you have studied the electronics modulation, you must have known as well. This is what is carrier and what is the envelope. Okay, so the phase velocity, in simple words, is written here that how fast the peak or crest of a wave move. Okay, phase velocity. Now the group velocity, how fast the overall wave packet or a pulse or energy, definitely there is energy when there is a pulse, moves. So here, this is your group velocity and here is your phase velocity. Okay. We can observe maybe phase velocity greater than group velocity sometime. It depends actually. So this slide, the purpose of this slide is the phase velocity, what is phase velocity, what is group velocity, to understand in simple animated way. Okay, now we move to the next slide. Mathematically, the group velocity here, you can see this relation, okay, and see your omega, this is k, okay, and this is your phase velocity, omega, this is k, okay. So wave vector actually, this k is a wave vector. Some cases can be wave number, but little wave number is a little bit different. So here, the group velocity and the phase velocity, they are equal. And this is the condition in the vacuum. And here, in a medium, there's a medium, any medium, okay. The phase velocity is greater than the group velocity. Phase velocity is greater than the group velocity. You can observe here in this animation that red is crossing the blue one. So the red is phase velocity. Even in the previous slide, you could have observed that phase velocity is moving ahead of the group velocity at certain period. Okay. So phase velocity can be greater than group velocity. And these are the mathematical relations which you must have learned in optics, basic optics or something like this. If here, if refractive index is same, N1 is equal to N2, so we have Vg equal to Vp. Okay. And what is here, if N1 is not equal to N2, then Vg is not equal to Vp. Okay, it can be like phase velocity can be greater than the group velocity or something like this. Okay, so you can use the same equation to confirm this one actually, this thing. Okay. Now, this phase velocity and the group velocity is necessary to know because it comes a lot. I mean, when you study the ultra short pulses and these kind of things. If you see the heading of this slide, you can see that group velocity dispersion, GVD. So what is this actually? This is your group velocity. If Vg is varying with color, then we call the group velocity dispersion. Group velocity dispersion, GVD. So here, you can see some difference here. Optical pulse in a transparent medium. Transparent medium, it can be any medium, okay. Even the water, or if you sleep or whatever it is. So when it passes through a light in a transparent medium, stretches, disperse, okay. So here, if you see here, this is a blue and red, two components are shown here. So that this is red and this one is, sorry, this is the blue and this one is the red. It's stretched now. You compare with this one, stretch. If it is like this here and it will move here, it will be like this. Okay, colors here. So this is the effect which is going on when you have broad spectrum. It's more prominent. Okay, and V is equal to C over N, the speed of light in a medium, you know already. And N actually, it depends on the wavelength. Usually we write like this, N is equal to N lambda. Here, if you see here, this one, C over N. Okay, this group velocity. And it's same thing here. In general, V is equal to C over N. So speed of light, refractive index. Okay, so it means when the light passes through a medium, the different colors, they move with a different velocity. Okay, so when they move with a different velocity, so that is why it dispersed. Okay, so like if there's a medium, red light will be here, maybe blue may come here. Roughly, I'm telling you, not exactly telling. Other colors may be here because of the different velocity. Okay, and it depends upon the refractive index and etc. Here, the same thing is mentioned here, that because of the group velocity dispersion, the longer wavelength, which is the red color uh, of the pulse, will propagate faster than the blue components, which are the last one, which is the tail actually, just shortest or shorter wavelength. So what will happen, that the pulse will be stretched. Okay, and this stretching thing, we call it chirp. Chirp. Okay, and chirp, this chirp actually, this word is very important, you will see later on. This chirp has to be compensated. Different color move with a different velocity when they pass through the medium because of the group velocity dispersion concept or phenomenon. And pulse stretch, blue slower, red faster, and we call it chirp. Okay, so this chirp we need to compensate. Okay, so if we cannot compensate, then laser operation like femtosecond or ultra short, ultra fast laser operation is not possible. Okay, we cannot get shorter pulse. Okay, so understand this thing. Now we move to the next slide here. How you see that the light is dispersed, stretched. Okay, chirp introduced. Again, I play here. You can see the beam or any light here on the left side. It passed through, moves to the medium, one medium, two medium, and it stretched. Okay, so the light, red is moving faster, blue is moving slow. That is why this stretch has happened, and this is the chirp. So chirp is introduced here. Okay, so try to understand again. Look at this animation here. Like there are two medium. First is passed through this medium here. Then it passed through this medium. Less stretch and then more stretch. Okay, and you can clearly see the difference. Okay, so this is how you can see this chirping effect happens.
Excuse me, sir. Please play it again.
Mhm. Yes.
Okay, sir. Thank
Okay.
you.
Yeah. Okay, so this is variation of group velocity with the color. We called it group velocity dispersion. Okay, and if we multiply group velocity dispersion with the length, then we call it group delay dispersion, GDD. Okay, look at the title of this slide. Okay. Variation of Vg with the color, like in the last slide, we call it group velocity dispersion. Okay. Different color move with a different velocity. And if we multiply this GVD with the length, like how long is a medium, then we call it grouplet dispersion. So this light is passing through 1 millimeter medium, 2 millimeter, 3 millimeter, 4 millimeter, 1 centimeter medium, glass medium, or whatever it is. So then we call it group delay dispersion. Okay? Keep remember this thing. This GVD and GDD is very important, and you have seen by yourself that when it is animated, how it affects. Okay, so now we move further. Below moving the velocity of the blue actually less than the velocity of the red, which is called the group velocity, you can say. So red is moving faster than the blue. No. So the same thing which I mentioned in the last slide, when the pulse passes through a material or any medium, transparent medium actually, then you have a chirp. Okay, what is this chirp? Keep remember. That is why later on will come the CPA, chirp pulse amplification. This concept will come later on. Okay, so here GDD is equal to what? Group velocity multiplied with the length of the medium through which it passes. Okay. So the red and IR is moving faster than the lower wavelength region. So like violet, blue, and ultraviolet or something, they are slower. They will move slow as compared to the front, like red or the infrared or something like this. And also GVD, group velocity dispersion, and GDD, they both are always positive because it cannot be negative. Okay. And GVD, this is the velocity. And when it passes through a certain medium, then we call it GDD. Okay. Keep remember this thing. So pulse, when it passes through the medium, 1 medium, 2 medium, 3 medium, then it becomes more and more and more and more stretched, longer and longer and longer and longer. So you don't get short pulse. Okay. So, I mean, if these two mediums, okay, if the pulse is like this here, then it will be like this. So probably it will stretch a lot. It can go to the picosecond or maybe 100 picosecond or something like this. So very important phenomena and very important to know about it and very important thing to compensate actually. Okay, so this chirp effect has to be compensated in case of if you want to generate the ultra short pulses. Okay. So now, till now, I'm saying we need to compensate. Till now, we try to understand what is this GDD, GVD, why color is moving with a different velocity or something like this, why did dispersion happen. Can we compensate it? Definitely, we can do it. And we have to. So that is why in the cavity of the femtosecond laser, ultrafast laser, you need a dispersion management. Here you can understand more how it disperses. The light is going, and when it passes through, before the dispersion and after the dispersion, you can see. It happened quickly, I mean, but you can observe. Okay. So before the dispersion and after the dispersion. This is also, I mean, to clarify you people that this kind of thing may happen. Now, compensation. How we can compensate? We can simply compensate by certain arrangement of the prism or the grating. And grating can be a transmittive type, grating can be a reflecting type. And how it is, I mean, you need to compensate the different colors moving with a different velocity. So you need to make arrangement that both the colors move with the same velocity. So you can use 2 prism, you can use 4 prism, you can use 2 gratings in a certain way, with a certain angle. Here, I'm not going to that detail what angle you need to set. The purpose was here to introduce or to tell you about these kind of things. So if you see this yellow portion here, blue and red, because they are moving with the different velocities, okay? So we have to make arrangement that red to cover less distance and blue to cover more distance. So at the end, both appear together at same time, okay? So like here, it's mentioned red to cover less distance and blue to cover more.
Sir,
Okay.
sorry,
Yes.
can I say something?
Yes.
Sir, in the last slide, we saw that red length color more difference.
Mhm. Which one? This one
So, yes,
or this one? This one?
sir,
This one?
yes. Whatever, this one or the previous one. Red is covering more distance.
Mhm.
So,
Red
is
is
it
moving
possible?
fast, not covering more distance, moving fast,
Yeah, moving.
faster than the blue.
So, sir, inside prism, will it cover also? Will it also move fast?
No, say it again. I didn't get your question.
Sir, I'm saying inside prism, like we have made some arrangements of
Okay.
diffraction rating.
Mhm.
Sir, inside red color will have high speed, so it will cover more distance inside the cavity of prism or compensator whatsoever.
Its velocity is
So
more, so it move faster.
it move faster.
Okay.
Uh,
And
yeah,
blue velocity is lower, it moves slower. Okay.
yes, sir.
So that is why blue is lagging and the red is leading. Okay. So
Sir,
in the cavity, what we do, just a minute, in the cavity, what we do, we use the prism arrangement to make possible that red to cover less distance and the blue to cover more distance so that they will become equal at the end.
yes, sir.
Okay.
Thank you. Yes, sir.
Right.
Thank you.
So here you can see in this
Sorry, sir.
grade.
Sir,
Yes.
I didn't understand it. Actually, the question was that the red color is faster, so it should cover more distance as compared to the blue, so that they meet at the final point at the same time.
No. Why so? If the blue is moving fast,
Yes,
if the blue is moving fast and the red is moving slow, so what we are, if you are, let's suppose it's Salman and you, if Salman is
yes,
moving fast and you are moving slow, how you people can meet
yes,
at
sir.
the same point, at the same time? How?
Sir, Salman has to cover the more distance than me, so that
No, Salman
we meet
has
at
to
the.
make slower. Salman should slow down to meet you.
Sir,
It's not
but
a
in the
matter of distance
compensator
here.
case,
It's not a
Sir,
matter of distance here.
actually, sir, want to explain it that the red light is moving same distance as the blue light, but the blue light cover that distance after 2 seconds.
I mean, you can assume the time.
Both have the same target.
Yes, both have same target, but the blue, because the blue is lagging, that is why it's stretched. And red is moving fast, blue is moving slow. So we want both these to be same. So that is why we give a less distance to the red and more distance to the blue. So this is the only possibility. Otherwise, if you give a more distance to the red, red will be more and more faster. It will be more stretching. Okay.
Sir,
Yes.
there is something else. Sir, when blue is already moving slow, then we make it to cover more distance, sir. Doesn't it mean
Yes, and slow to red. You have to compare both the colors, not independently.
Sir, how we does that prism?
Here you are talking about optical path length. So for optical path length,
Actually, you can see this figure here on the right side, left side.
I can see on both sides, sir.
You can see on the right side. So
Yes, sir, I can see.
what you can see here? Tell me.
Sir, I see that blue color is covering more
Yes.
distance when its speed is slow, and red color is covering less distance when its speed is high.
Yes. So here you see this is a less distance and this is a more distance here. Okay. So that we make it possible they to meet at the same point here.
Is it same point or different point?
It's the same point. Same point means they are not merging to each other, but the point they're reaching at this point because here this distance is longer. In case of red, this distance is longer. In case of blue, this one is shorter. Okay, this one is shorter for the red. This one is shorter for the blue. This one is longer for the blue. This one is longer for the red. Okay. Try to understand, okay, we have to move forward.
Yes,
you can go through and we can discuss in the next lecture. Okay,
yes,
so
sure.
same thing you can do with the grating and the same thing you can do with the prism compensator. In the next slide, you will see more actually than how it can be. It can be done with the two prism. Like you can see here, 4 prism are used. This is the red color and this is the blue color. So the red color make it to pass through more denser region as compared to the blue. Blue is passed from the peak, so less denser region. Okay, so then you make it possible to combine here. Uncompensated input pulse. Okay, so uncompensated input pulse means that pulse is already stretched. Okay, and we are using 2 prisms here. But 2 prisms you cannot use like in a random way. There is certain arrangement. Actually, there are equations, mathematical equations to how to set this angle. So the light passed through here. Okay, it spread, dispersed. This is the red one, and this is the blue one or ultraviolet. Okay, and now it passed through the other prism. From the first prism, it passed through the edge. Okay, and from the second prism, it passed through from the near the base. It's not passing through from the edge again. Okay, also one of the reasons that it's dispersed. And this is the retro mirror. So from here, it's reflected back and retrace the path. Okay, and at the end, you get this one. How? Now I will upload this lecture. You try to understand how this thing is happening. Even you can use if you know some mathematical equations and how this thing is happening. We read how to make the red slower and how to make the blue faster. I mean, metaphorically, you are not making them to move faster or lower. You are inserting something in their way. Okay, you are utilizing this concept that the velocity of the light and each and every color have a different velocity. So how we can compensate they to reach at the same time? Okay, you can also take some other examples like different cars or something like this. Okay, we can discuss in the next lecture as well. Okay, now how to generate the femtosecond pulses or the ultra short pulses. This scheme, if you see here, this we call oscillator. From here, the pulses are generated. This is a cavity. Okay, this is a similar cavity like this and the gain medium here. Only difference is that you see here these two prisms to compensate the dispersion inside the cavity. Okay, you cannot insert here because this portion actually, this portion where the pump beam is focused. Okay, pump beam is focused to where the gain medium, and so the gain medium, the pump is supposed to be focused at the gain medium. So the gain medium, you know that the basic principle that population inversion, okay, and stimulated emission, these things happen. And in this cavity, the photons are generated and they start moving. But they are not start moving that only in this portion. They start moving like this. Here, here, and here, 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 all the way. Okay. So this cavity is not that simple, what we have learned for a basic laser. Why? Because you need to insert the prism or any other arrangement so that you can manage the dispersion. And you need to focus, and it's not like a medium is not like in the form of a rod. It's a crystal. It's a very small size. And you need a green light or pump source to focus on it. Okay. So this kind of arrangement is used. It's a typical oscillator for the titanium sapphire crystal. Titanium sapphire femtosecond laser, titanium sapphire based femtosecond. Duration of the pulse is 100 femtosecond. So 100 femtosecond pulse appear after every 100 megahertz. Okay. Or you can convert into the time. Okay, so there are some more slides yet, but I will finish here because I think it's pretty late there in the other part, Pakistan. It's 10 o'clock or 11 o'clock? In Pakistan, what time is now?
10
10
o'clock.
10 o'clock. Okay. So you want me to continue or it's enough for today?
But I have no issue. You can continue.
Who has the issue? I mean, is it okay to continue or you people want me to stop here? For you is okay. Sorry? Sorry? Nargis?
Yes, sir.
You are saying something.
Very interesting.
I couldn't hear properly. Say it again.
So it's okay for me to continue.
Okay.
Am I audible?
I mean, not.
Hello?
I mean, sometime, but it's not. I'm not able to understand what you are saying.
Sir, I am saying it is okay for me to
Okay.
continue. The
Okay.
lecture is very interesting.
Okay. Okay. So this is the basic scheme. Salman, for you is also okay, or you want to go to sleep now?
What, sir?
For you, it's okay to continue, or
No, sir. I think it should stop now because I have class at 8 a.m. tomorrow,
okay, okay,
and I have to prepare lecture for that.
okay, okay. A few more slides, and then we'll finish. Actually, this is the basic scheme for the generation of the femtosecond pulses, and this is a typical, like in the last slide, this is a typical scheme for the
Hello, sir.
Sorry.
My internet interrupted. I didn't hear you.
Okay, it's okay. I mean, if you want to go, you can.
Said something?
You can leave. I didn't say anything.
Okay, sir.
Okay, okay.
Okay, sir.
Okay. Okay, so here, do you have prisms? Okay, you have end mirror here. This is end mirror actually. This is output coupler. And you have cavity mirrors here as well for the pump beam. And you can see here the light is, the color is also shown that the red is supposed to pass through near the base and the blue is supposed to pass through near the edge of the prism. So there is no, I mean, like the shape of the cavity is like this, as I explained, because we need to introduce the dispersion management for the dispersion, the prism or whatever the arrangement. So that is why the cavity becomes a little bit complex. And when this cavity, and this cavity actually, depending on the arrangement of these two prism pairs. Normal case, I told you that the conventional one, this kind of oscillator, standard oscillators, usually they operate in like around 800 nanometers. Pulse duration is around maybe 25 femtoseconds. Pulse energy can be around 5 to 10 nanojoules. Repetition rate usually 80 megahertz. Okay. And all these things are depending upon the length of the cavity, the whole length. That design consideration will also come, but that will be later. And the pump source is a green one, and that is, it can be like starting from 480 to something like 530 or something like this. And it can be pumped with whether you can use this ND YAG, second harmonic, or whether you can use this CW YAG laser. Diode pump solid state, also possible diode pumping. This is the experimental titanium sapphire laser oscillator. Okay, same scheme, what you have seen before. So here, if you see, this arrangement actually is for the pump. The pump beam pass through here and focused here. And this crystal is Brewster angle cut. Okay, 12 point. Like this angle is supposed to be 12.3 degrees. Okay, and these are the mirrors. One is 90%, other one is 100% where you want to take it, the output. And these are the prisms. You can understand here. Okay, and you can see here. And this is the crystal. How does it look like? This is a very small size actually. And it can emit from 650 to 1100. Okay. And this kind of arrangement actually This kind of arrangement is made because of this B cut. It's called B cut, Brewster cut crystal. Why do we need the Brewster cut crystal? This certain angle to compensation of astigmatism, especially in the oscillator. In the amplifier, we can use a straight, not be any kind of Brewster cut or something like this. But in case of where we generate the pulses like oscillator, then it has to be Brewster cut for the to avoid the astigmatism or something like this. This is the output you see from the oscillators. That this is the oscilloscope image, and this is the spectrum. This is the output spectrum. This is the wavelength here. Okay, and you have the intensity on this side. So you can see it's pretty broad spectrum. It's from 700 to around 880 or something like this. So it's around 700 to 80. So it's around 200 actually, 200 nanometer. So 200 nanometer spectrum. Okay, so if we are not supposed to compensate the dispersion, probably we cannot get the femtosecond pulse. Okay, 200 nanometer is a lot. It's a big spectrum. And definitely when it passes through the medium, then it will stretch by short. So one of the things for the femtosecond and ultra short pulses that these prisms are necessary, prism or this kind of other arrangements. Other arrangement, there are some other arrangements, but I'm not telling about these arrangements because that is very advanced kind of things. Simplest one to use a prism. And we should not use any kind of dispersive elements. Dispersive elements mean that any kind of glass slab or any kind of mirror, not mirror, any kind of lenses, so that when the light passes through, so it disperses. So avoid these kind of things for the femtosecond laser. Okay, so let's stop here. We'll continue in the next class. And the next class, we will see the design consideration. When we make the oscillator, what three formulas are necessary? Okay, that three formulas are necessary when you design. And there are something which is related to the dispersion compensation also. So these things we will study, and also we will move toward the what exactly the meaning of CPA system and then amplifier. And then at that stretcher and compressor also we'll discuss. And that will be probably towards the conclusion of the whole this coursework. Probably we have maybe more 3 or 4 lectures or something like this. It depends. So probably if you have any question, you can go through and we can discuss in the next class or lecture. Okay. It's okay now?
Yes, sir.
Okay then. Okay, thank you very much for attending, and please go through this lecture, and I hope you will understand. Or if not, then you can ask me in the next class.
Yes, sir, sure. Thank you, sir.
Okay, thank you very much. Thank you for joining. Okay. Hope to see you in the next class. Okay. Bye bye. Allah Hafiz. Bye bye.
Allah Hafiz.
Thank you, sir. Bye.